we're ready to start talking about the addition reaction mechanisms. Our first mechanism is going to proceed along something we call the carbocation pathway. And we're going to have two different types of alkene reactions that will proceed according to this mechanism. The first one is hydrohalogenation. This is where we're going to be adding both a hydrogen and a halogen. So what this means is I'm going to have some kind of alkene. I'm going to react it with some kind of hydrohalogenetic acid. Did I just make up that word? Which is going to be chlorine, bromine, or iodine. And we're going to get the hydrogen bonding to one of the carbons and the halogen bonding to the other carbon. So let's take a look at what this mechanism actually looks like. Keeping in mind, we're going to know that it's going to work according to this mechanism because this is going to be our reactant, either hydrochloric acid, hydrobromic acid, or hydroiodic acid. Hydrofluoric acid will not be available because fluorine is a little bit too electronegative. It doesn't react the same. So in order to understand this mechanism, I've got the substrate here drawn up along with my hydrochloric acid. We're going to use chlorine as our halogen in this one. The way that this is different from other mechanisms we've seen before is that the substrate is actually going to be acting as the nucleophile. Specifically, that double bond is going to be acting as the nucleophile. Remember, a double bond possesses both a sigma bond, which is going to be between two carbons, and a pi bond that is existing above and below. That pi bond has a lot of electron density. Let's draw a little model to check that out. So I've got a model drawn here that is really a close-up snapshot of this substrate. I've got my alkyl groups still sticking out on either side. We're not taking too close of a look at those. We don't care. They only have sigma bonds. But I've got my pi bonds and sigma bonds of that double bond located here. Notice the sigma bond between the two carbons. This is going to be a smaller area. These two electrons are shared between these two carbons. They're going to be shared pretty equally. And these two electrons are very easily attracted to those carbons. They're nice and close. However, the pi bond, while that is existing, connecting these two carbons above and below, it does have a greater distance away from these nucleuses. So it is not going to be as strongly held to those carbons. So the electronegativity of pi bonds is actually going to be greater than sigma bonds. And that greater electronegativity is going to allow it to reach out and grab another positive charge, which we can see in a hydrogen. Hydrogens are going to be a very positive charge, and if it gets too close, this pi bond is going to be way more attracted to that hydrogen than it is to its host carbon. So now that we've seen that, let's go ahead and start drawing our arrows. Remember, we're drawing our arrows from our area of greater electronegativity, basically from our electrons to what they're reaching out and grabbing. So we're going to draw an arrow from our double bond to our hydrogen. Okay? That's our first arrow. Our second arrow is that this hydrogen needs to let go of that chlorine. When it does that, that chlorine is going to keep that bond. So this hydrogen lets go of its bond, the chlorine keeps the bond, and there's our second arrow. So after this, we're going to get a hydrogen attached to this carbon specifically. We'll talk about why in a minute. And we're going to get this chlorine all by itself with a negative charge, and this carbon right here will have lost a bond, becoming a carbocation. So next up, we see that chlorine anion is floating around all by itself without a positive charge to call its own. And we see this hydrogen bonded to this carbon. It bonded there because of Markovnikov's rule. It is going to have an easier time binding to this carbon because this carbon has more alkyl substituents. It is going to be easier for this carbon to hold on to that positive charge. It's going to be easier for this hydrogen to fall in and bind to a carbon that has more hydrogen substituents because they're smaller, they take up less space. It is easier for the hydrogen to fit in there. But once this happens, we have this second step. So we do have several distinct steps here. So we have a step 1, a step 2, and in our step 2, this chlorine is now a negative charge that is attracted to this carbocation. So we're going to have this chlorine attack as the nucleophile this carbocation. And once it does that, it is going to bond there, and we're going to get our final product. So here's our final product from the hydrohalogenation of an alkene. This product is going to follow Markovnikov's rule, and therefore we are going to be regiospecific anytime that rule comes up. Which means if on one side of this double bond I have more alkyl substituents, or one side has more bonds to hydrogen, then I'm going to have a very specific way that this hydrohalogen is going to bond to it. So I've got 4 more alkenes drawn up here. Let's just take a second to look at that regiospecificity. In which of these alkenes is Markovnikov's rule going to factor in? As in, what I mean to say is when is it going to matter which carbon the hydrogen binds to first? Well, we look at this first one. If I've got a hydrogen around here trying to pick which one of these to bind to, I'm going to choose which one has more hydrogens that it's already bound to. This carbon right here has 2 of its bonds connected to this carbon. Therefore, it's going to have 2 hydrogens. This carbon up here is more substituted, so it's got 1, 2, 3 carbons that it's bonded to, and it's only got 1 hydrogen. So this hydrogen here that's binding here would be bound right there. That's the carbon it's going to pick. So that would be regiospecific. It's going to have one specific constitutional isomer that's going to come out of this. How about this one? Is this carbon or this carbon more substituted than the other one? No, they have the same substitution. This carbon has 1, 2, 3, 4 bonds all to another carbon. This one has 1, 2, 3, 4 bonds all to another carbon. Neither of those carbons are attached to any hydrogens. And so if I have this alkene reacting with a hydrohalogen, too many H words, then the hydrogen is going to go to either of these carbons. It's not going to make a difference. And in this case, we would not have regiospecificity. However, this is also a balanced alkene, so it wouldn't actually make a difference either way. The next one, I can see that this carbon is bonded to 1, 2, 3, 4 other carbons. This one is bonded to 1, 2, 3 other carbons and 1 hydrogen. So we can see that this would be Markovnikov. The hydrogen that gets pulled in is going to attach to this carbon because there's more hydrogens there. Last one, we've got a double bond here. Both of these carbons are secondary substituted. They are both bound to 1, 2, 3 other carbons, regardless of where this sits. So I could have 2 results out of this alkene. I could have my hydrogen pick here, or I could have it pick here. It's not going to make any difference. So this would not be regiospecific. There are actually 2 constitutional isomers I could get out of that. So when Markovnikov's rule is going to take effect, we're going to have very specific regiospecificity. When Markovnikov's rule does not take effect, when we have the same amount of substitution on either side of that double bond, it's not going to take effect, and we're going to get a mixture of both isomers. The second reaction type that we're going to be looking at here is the acid-catalyzed hydration of an alkene. This is going to follow that same carbocation pathway. So we're going to be using the same mechanism, but it's going to look a little bit different because we have some acid catalyzation happening first. Now, this reaction could happen without an acid catalyst. It would work the same way. It would just be extremely slow. And so it's most often done with an acid catalyst. So we're going to see why in just a moment. By definition, what that acid catalyzation is going to really be giving us is hydronium ions, H3O+. In the past, we've looked at acidification as just a hydrogen ion, cation, just floating around in the solution, just as a regular H+. In reality, that doesn't make it very far in the solution. It's going to get picked up by something. It's extremely positive, and it doesn't have an electron cloud around it to stop anything from snatching it up. So anything that can will pull this up. What's very good at pulling it up is water. So water will make a hydronium ion. If we were in a solution of ammonia, we'd be getting ammonium, things like that. But what we're going to be working with here is hydronium. This is really going to be the other reactant that we're going to be working with. So we've got our substrate of our alkene, and we have hydronium. Those are going to be working together. So once we've got the hydronium, the sulfuric acid has done its job, and we're not really going to pay any more attention to it. So with all that said, at the end of the day, what we're starting with is the alkene and the hydronium ion. The alkene's pi bond is going to be attacking. It's going to make a nucleophilic attack on one of these hydrogens, which will then give up its bond with that oxygen. So once again, that hydrogen got picked up by that double bond, by that pi bond, and now it's going to be sitting here on this carbon. I know it's going to go to that carbon because that's the one that had more hydrogens to start with. Remember, Markovnikov's rule. So once this happens, I've got this carbocation here. This carbocation is then going to be very attractive to the oxygen. That oxygen is now going to act as the nucleophile, and it's going to make an attack in order to bond to that carbon. So now what I've got is this alkane with a water molecule attached, a whole water molecule attached to it, floating around in a solution full of water. So it's probably not going to stay a water. It's going to become an alcohol because this hydrogen is going to have a hard time holding on. This oxygen is going to be more tightly bound to the whole alkane and one of its hydrogens. So another water molecule can come along and pull away that hydrogen, giving us our final product. So our final product, we get an alcohol along with a hydronium ion being regenerated. So we used up an entire water molecule, but we still regenerated our initial hydronium. So this reaction could happen again with the other alkenes that are in the solution. After examining those two mechanisms, we can now see that in acid-catalyzed hydration and in hydrohalogenation, we're going to be following the carbocation pathway for our mechanism. Within that mechanism, we are going to have regiospecificity using Markovnikov's rule. Wherever that's applicable, we will be regiospecific. What about stereospecificity? Well, we didn't talk about this, but because of how the mechanism works, that initial hydrogen is able to attack from either side, and once it's attacked, it's able to be attacked from either side of the molecule, and once it's bonded, it doesn't really make a difference what side of the molecule the water or halogen attacks from. So we're not going to see any stereospecificity. We will see both syn and anti-products of both types. So we might see the hydrogen and the halogen pointing forward, backwards, opposite ways, and we might see the alcohol and the new hydrogen pointing forwards, backwards, both ways, opposite ways. So there is no stereospecificity that you need to keep in mind here. We will have hydride and alkyl shifts occurring whenever possible. So when we hit that step 2 and you have that carbocation, you should always pause and think to yourself, could this have a hydride shift to get a more stable cation? If it can, it will. So let's take a look at an example of a molecule that will have a hydride or an alkyl shift. So this is the molecule that we're starting with. In order to make sure we're keeping track of Markovnikov's rule, let's just take a moment to identify where our hidden hydrogens are. And let's put those in a different color. Let's put those in green. I've kept the hydrogens that are on these two carbons on the ends hidden because they're not going to participate in any way, shape, or form in this reaction. But we should be able to identify how this reaction is going to proceed. Based on our mechanism, our pi bond is going to be attacking the hydrogen, and that hydrogen is going to attach here, forming a carbocation here. So let's look at that mechanism. So once again, our first step is our pi bond attacking our hydrogen, and our hydrogen letting go of its bond with the iodine. So that bond going straight to the iodine. Now, normally, our iodine would immediately attack this carbocation, but this carbocation could have a hydride shift. It's very possible. And if it can, it will. So we can see that this is a secondary substituted carbocation, but we have right next door the opportunity to have a tertiary substituted carbocation. We only see this because we followed Markovnikov's rule, because we got this carbocation in the correct spot. It's got to be here. It would not appear here. It's got to be here. So when we have this carbocation, it's going to have a hydride shift over to here. So this hydrogen, and I drew that in a kind of a bad spot, is going to move over to here. That's going to be our next step. So we need to keep those hydride shifts in mind. So now that we have our hydride shift occurring, we can see that now this carbon has 2 hydrogens, this one has 3, and this is where our carbocation is. Where is that iodine going to bond to? It's still going to go after the carbocation. And so I get a very distinct product here because of that carbocation shift. Let's draw that arrow a little better. So this iodine is going to bond to that carbon, and we're going to get a distinct product. With all of my hydrogens hidden, I get an iodo group on this alkane. So let's go ahead and draw out what the wrong answers would look like if we had forgotten to do this carbocation shift. So I've got the 3 possible products we could have seen if we went through this. The top one is the correct product, which takes into account Markovnikov's rule and that carbocation stability resulting in hydride shift. The second one here, this did not take into account the hydride shift. And we would see that our iodo group gets bonded to a different carbon. This is important. So this one would be incorrect. And we can see this one did not take into account Markovnikov's rule. And we see the iodo group bonded all the way to the end carbon, which is not where it would bond. It would not want to go there because this would get taken up by that first hydrogen. So this is also not correct. This is the only correct answer. It has a specific isomerism that we don't see any of the other products. We only see this product. So as you're going through the carbocation pathway, make sure you're keeping in mind the hydride and methyl shifts and Markovnikov's rule.